Okay, so let's finish our discussion introducing electronic structure theory, also known as quantum chemistry. What I'd like to do now is do a quick tour through some of the methods of quantum chemistry, and then in future talks we can discuss them in more detail. Okay, so first off, let me just remind us what equation we're solving. We're going to solve h equals E psi, the time-independent Schrodinger equation, but we're going to do that by first invoking the Born-Oppenheimer approximation. So that means we're really solving for the electronic Schrodinger equation, which is going to give us electronic wave functions and electronic energies. And then, if we need to, for our application, we then solve for what the nuclei do on this potential energy surface generated by the electrons. So this is the central equation that we're focused on when we talk about quantum chemistry. So how do we go about solving this equation? Well, it's still a very complicated one because the Hamiltonian has a kinetic energy operator that takes second derivatives, and there's a lot of coordinates going on. We talked about how the wave function is a function of all the Cartesian coordinates and the spin of all the electrons. So Douglas Hartree had a proposal. He said, let's just try a product of orbitals, and orbitals are just single particle functions. So let me go ahead and introduce some new coordinates or new notation so that we can properly know what the coordinates are and how we're dealing with them. If we just had Cartesian coordinates to deal with, then this Hartree product idea would mean that electron 1 goes in orbital phi 1, electron 2 goes in orbital phi 2, and you just have a product of these one electron functions, which is what an orbital is. And I could collapse x, y, and z into a vector r just for ease of notation. However, that ignores the spin, and so kind of following Szabó and Oslin, if we imagine there's a spin coordinate, omega, then let me introduce vector x, and vector x is not little x, so little x is a Cartesian coordinate, vector x is a collection of coordinates. It's just going to be the x, y, and z coordinates of a particle plus the spin coordinate omega. So that's what bold x or vector x is. And again, just to remind myself, if I'm talking about an orbital that depends on spatial coordinates or spin coordinates, I'll use a different notation for the orbital. So I'll use phi to mean a spatial orbital that just knows about the spatial coordinates of an electron, and I'll use chi to mean a so-called spin orbital that also knows about the spin of an electron. Okay, so whether you're talking about spatial coordinates or spatial coordinates plus spin coordinates, this is the Hartree product idea. Just multiply a bunch of orbitals by each other. All right, well, that's certainly an idea. Does it work? Well, no. Even immediately off the bat, there's a gigantic mathematical problem with this wave function, and that is that electrons are supposed to be indistinguishable particles mathematically because they're fermions, and if you interchange two fermions in a wave function, the wave function is supposed to be the same apart from being multiplied by -1. And that's called the anti-symmetry principle. So for example, just to have a wave function that's a function of two electrons to make it a little easier, if I had this wave function, this would be a Hartree product. It's a product of two orbitals. And if I interchange these two electrons, then the coordinates of electron 1 become the coordinates of electron 2 and vice versa, so I sort of swap x1 with x2, then this would be the result. Now, electron 1 is in orbital 2 and electron 2 is in orbital 1, which is not the same as the above, and nor is it the same times a minus sign, which is what you're really supposed to get for electrons. So what can I do? Well, I can sort of force this to work by construction. If you think about it a little bit, you would eventually come up with this suggestion that the wave function could be I'll put 1 over square root of 2 just to keep it normalized, because we want the integral of psi star psi equal to 1. And if the orbitals are normalized, then I would need this 1 over square root of 2 for this thing to be normalized. But in brackets, I've got the 2 terms I had on the previous slide. Here, electron 1 is in orbital 1, electron 2 is in orbital 2. And then I put a minus sign, and I put this other term where I had flip-flopped which electron is in which orbital. And you can see that if you start with this, and then if I flipped x1 with x2 here, and then also here, to get overall psi of x2, x1, that winds up being the same as the original one, times a minus sign. You could just write that down and literally interchange the x1s and x2s, and you'd immediately see this term turns into that with a minus sign, and this term turns into that with a minus sign. So I do get the same thing back times a minus sign, which is what I want. So I've found a way to dodge this problem with the Hartree product. All I do is I write the Hartree product, and then I subtract a term where I flip-flop the electrons, and then that thing, by construction, does satisfy the anti-symmetry principle, which is this line. You want the interchange of 2 electrons to give you the same wave function back times a minus sign. So this one's okay. Should we use this one? Well, before we talk about that some more, let me point out that a shorthand notation for this wave function is this. If I write it as a determinant, then you'll remember for a determinant, if I expand a 2 by 2 determinant, it's just the diagonal term, chi1 of x1 times chi2 of x2, minus going up the other diagonal, chi1 of x2 times chi2 of x1. And so that's just the same as this thing I had here. So this is kind of a convenient way to write this, and it maybe gives us a hint how you would write more complicated ones that involve more than 2 electrons. And so this was the idea of John Slater, the Slater determinant, where I make a determinant just like we were talking about, but now if I have n electrons, then I'll have an n by n determinant, and you'll notice that each column is a spin orbital. So the first column is spin orbital 1, the second orbital is spin orbital 2, etc., up to n spin orbitals if I have capital N electrons. And then each row is an electron. So here I've got electron 1 in row 1, electron 2 is in row 2, etc., etc. And this, if I expand out the n by n determinant, will give me n factorial terms, and those terms will be generalizations of what I did on the previous slide. Each term will swap 2 electrons with each other in terms of which spin orbital the 2 occupy, and then I'll get a minus sign for each of those as well. The minus sign also comes out of, if you remember a little bit about determinants, if I swap any 2 columns of a determinant, I'll get a minus sign. So I generate all possible arrangements of the electrons among those spin orbitals, and every time I do a swap from some starting configuration I had, I get a minus sign back, and ultimately that means the electrons are indistinguishable. I can no longer tell which electron is in which orbital because I get all the possible arrangements, and I get minus signs popping out as appropriate, so that the total wave function gets a minus if I swap any 2 spin orbitals. Now this does satisfy the anti-symmetry principle, so we like it instead of the Hartree product. It's still a somewhat simple form. You might think it's kind of complicated, but in the grand scheme of things, you could have more complicated functions. So there's no guarantee that this is going to be adequate to give us accurate results. We'll talk more about that. But at least it satisfies the anti-symmetry principle, which is a good place to start. Now, writing down these determinants over and over will get really tedious if you were deriving some equations, so nobody does that. We have a little shorthand where you just use a ket symbol, which we use for a wave function, and then we'll just list the spin orbitals. And it's implied that we're going to throw these spin orbitals into a Slater determinant like this, and then we'll get the anti-symmetry. So that's a shorthand. And in fact, even writing these chi's over and over gets tedious as well, so we can drop those and just write a ket symbol with the name or the index of all the spin orbitals inside the ket, and then that'll tell us how to construct this guy. Okay, Now, although this satisfies the anti-symmetry principle, these chi functions, these orbitals, where do I get them? They got to come from somewhere. I need some kind of rule or equation to give these things to me. All right, so how am I going to get these orbitals? Well, we're going to appeal to the variational theorem. And this is something you may or may not have encountered before in quantum mechanics. But the variational theorem tells you that if I have an approximate wave function, then the energy I would compute for that approximate wave function is always greater than or equal to the true energy of the system. So, how do I compute an energy in quantum mechanics? Well, if it's the electronic energy I'm talking about, then it's the average value of the electronic Hamiltonian for whatever state that I'm in, psi. Okay? And this, you may remember, is just decoded this way if I'm doing integrals. It's psi star of the times h electronic, or whatever operator I'm working with, times psi. And I would wind up acting h on psi, getting some result, getting the overlap of that with psi star, integrating over all space. And this gives some result, whatever it is, depending on your choice of psi. But the theorem tells you that for any choice of psi, the answer you get here must be greater than or equal to the exact energy of the system. And E0 just denotes the ground state I'm talking about here. So, and this only takes a few lines to prove. It might be surprising to you. You might think, well, gee, I could cook up a really strange looking wave function and I bet I could get a lower energy. It's mathematically impossible, and it doesn't take but a few steps to prove it if you sort of go about it the right way. It's a few lines. At any rate, let's just take this as a given, and if we know this, then that suggests an approach for coming up with reasonable approximation psi. We can try different ones, and whichever one gives us the lowest energy must be in some sense closer to the right answer, because we know we can never overshoot. So we'll try or vary different psis and get one that gives us the minimum possible energy, and that's the one that we'll go with. And what are we going to vary? Well, there are infinite possibilities, because you could cook up infinite functions. But we will insert the Slater determinant here for psi. And what are we going to vary as our parameters to try to minimize the energy? Well, the orbitals. We're going to keep tweaking the orbitals that go in as the columns of that Slater determinant until we get a minimum possible energy, and then we'll call that the best that we can do. And that is where we get the orbitals from. The orbitals are going to be chosen as those that minimize the energy, the average energy, of a Slater determinant. Okay. And this approach was proposed by Douglas Hartree and Vladimir Fock, and so that's why it's called the Hartree-Fock method, or the Hartree-Fock Molecular Orbital method. Molecular orbitals that most chemists and physicists and biologists, etc., have heard about come from this procedure. This is where they come from. So, first, we invoke the Born-Oppenheimer approximation. We usually don't even say this because we just assume everybody's going to do that before we even get started. Then we're going to say, all right, we're going to assume our wave function is a single Slater determinant. Are the exact wave functions single Slater determinants? Well, no, in general they're not. So this is an approximation. Then we're going to solve for the orbitals that give me the minimum possible energy for that Slater determinant using appealing to the variational theorem, and if you do this, it's called the variational method. And it turns out this is not obvious at all, but with a little bit of work, you can wind up convincing yourself that this procedure is the same mathematically as assuming that each electron feels the average electron distribution of all the other electrons. Okay? And so the electrons do interact with each other in Hartree-Fock theory, but only in a kind of a washed out, averaged out kind of sense. You miss instantaneous correlations of electrons. So it's not going to be perfect. Now, how do I come up with the orbitals that minimize the energy? Because even for a single particle function like an orbital, there are infinite possible functions I could try. So how do I know which ones to try? Do I try all infinite numbers of them? Well, obviously not. So what we do, and this is an idea introduced by Rotan, is we say, well, I've got some orbital and I'll have different orbitals, so I'll put a subscript on them to tell me which orbital we're talking about. In here I'll talk about spin orbitals, but you could talk about spatial orbitals as well if you wanted. Each orbital, chi I, is going to be a linear combination of some fixed functions. Who gives me these fixed functions? Well, Rotan or somebody has got to cook up some functions for you to use, and we'll call these basis functions because they're fixed. They're given to you by somebody, or you'll have to make some up. There's a finite number of those, k, of these basis functions, and I'll put a tilde so that we'll know which ones are the basis functions and then which ones are the actual orbitals. So basis functions with tilde, and each orbital chi I will be a combo of these, and the mixing coefficients I'll call C mu I. Okay, so that's the idea. That's all we're going to do. We're going to plop this into the equations, this expansion, and then vary these C coefficients, those are the variational parameters, until I get the minimum energy of the Slater determinant made out of a set of these chi I's. Okay, and obviously doing linear combinations of things, you can represent this set of coefficients as a vector or a matrix, and that gets us into linear algebra, and that's a good thing if we're trying to implement on computers. So that seems promising. Sometimes if you do Hartree-Fock this way with this basis set, it's also called linear combination of atomic orbitals dash molecular orbital theory. It's the same concept. You see this phrase sometimes in some of the textbooks. I think more recently people have kind of moved away from that notation and they just call it Hartree-Fock theory, which is a little easier to say, but it's the same idea. And this is a little more specific in calling out the important role of using these fixed functions if you're going to do it in a practical sense. Now, what do these functions look like? Well, if you're a physicist, you might use plane waves, especially if you're a solid state physicist, because you're describing a periodic system, and so plane waves make good sense for describing something like that, although sometimes you have to use a lot of them, which is a drawback. If you're a chemist or a molecular physicist, you'll tend to use atom-centered Gaussian functions. Okay, so that's all I'm going to say about Hartree-Fock for right now. I'll do another lecture where I explain that in a lot more detail. But let me just now introduce briefly some other things you could do in quantum chemistry besides Hartree-Fock molecular orbital theory. One of them is, one class of them is semi-empirical methods. And these are methods that start from the Hartree-Fock equations, but they take some of the time-consuming parts of that, particularly the two electron integrals, and they eliminate those or replace them with terms that are easier and faster to compute, thus speeding up the calculation, although at sometimes reduced accuracy. And so if you've heard of methods like Mendo or AM1 or PM3, these are all semi-empirical methods. They have some quirks, they have different deficiencies depending on the problem that you're looking at. Like Hartree-Fock, they don't do a very good job of explaining or describing accurately weakly bound systems. And they require some parameters like force field methods. And occasionally you'll maybe want to try a semi-empirical method and you'll find out for your system the parameters aren't available, which can be a drawback. Now, if I go in the other direction of trying to be more accurate than Hartree-Fock, then there are various possibilities. And I've mentioned already that Hartree-Fock is just an approximation. Let me remind you what the sources of error are. One of them I've mentioned, maybe one I haven't yet. First off, you are assuming a single Slater determinant, which I mentioned winds up being equivalent to assuming each electron only sees the average charge field of the other electrons, which is obviously an approximation. And the other one, when we introduce this basis set, as Rotan suggested, we, of course, use a finite number of functions for that. And anytime I use a finite number of functions, I may not be able to exactly describe what the quantum mechanical system really wants to do. And so I have a source of error there as well. But even if I were to use an infinite basis set somehow, hypothetically, in the Rotan's trick, I would still be left with this assumption number one. So either way, Hartree-Fock is not exact. Certainly error number two could be largely solved by just using bigger and bigger and bigger basis sets. Error number one requires us to do something different. One approach is I could shift over to density functional theory, which in principle is an exact theory. In practice, no one knows how to do that exactly, and so one winds up using approximations. Sometimes people talk about density functional approximations, which is what you do when you're actually trying to use density functional theory in a real calculation. DFT certainly can be more accurate than Hartree-Fock, even if it's not exactly correct the way we know how to implement it now. Or you could go to what are sometimes called post-Hartree-Fock methods, also called electron correlation methods. The error in the Hartree-Fock energy is sometimes called the correlation energy, because what you're primarily missing is the fact that electron motions are correlated with each other. What one electron does influences the other electron, and you partially capture that at Hartree-Fock because each electron sees an average of the other electrons, but that's not really enough to fully capture this effect. And the error in the energy is sometimes defined as the correlation energy. Just as a caveat, Hartree-Fock also sometimes has a big problem if you're trying to break a chemical bond. It's not particularly accurate for that. If you had a diradical, which is kind of a molecule with a permanently broken bond, that's not particularly accurate with Hartree-Fock. Transition metals, if you have unfilled D or F shells, it's not particularly accurate. These problems are all connected to each other theoretically due to the presence of many states that have very similar energies, quasi-degenerate states. So let's talk about how accurate Hartree-Fock is. Well, bond lengths are on average around plus or minus 0.02 angstroms off, which is okay for a lot of applications. Maybe not if you're trying to help out a spectroscopist, but otherwise sort of within sort of chemical reasonableness. Bond angles within about a couple degrees, similar comments as above. Vibrational frequencies within around 10 or 11%. Sometimes there tend to be a little bit on the high side, but not always. Dipole moments within about a third of a dBi. Dissociation energies are not accurately captured by Hartree-Fock. They could be off by maybe many kilocalories per mole, and that is unfortunate, but the error cancellation isn't very good for dissociation energies. So you get what's a very reasonable method, but certainly not a super accurate method. Let me briefly introduce some of these other approaches I mentioned besides Hartree-Fock and semi-empirical. So density functional theory, what do you do there? Well, you kind of shift your focus away from a wave function, which is very tedious to deal with, especially because it's a function of 4n coordinates, if n is the number of electrons. And instead we say, let's just work with the density. The density is just a function of x, y, and z coordinates in space. Maybe there's a spin-dependent part. but that's much simpler and easier as a function. And it turns out there are fundamental theorems telling you that the density can get you all the same things that the wave function could. So it's really useful. It's a variational approach like Hartree-Fock. So what you do now is you minimize the energy with respect to the density instead of the orbitals. And this function that tells you what's the energy for a given density, it's a function of a function, and that's what a functional is. It's just a function of a function. The problem is we don't actually know the exact functional, so we don't have an exact density functional theory, although it's exact on paper and in principle. Because we don't know this functional, it's not exact in practice. And so therefore many folks have invented a lot of approximate functionals, and sometimes these are called density functional approximations, which can be very useful, and some of them are rather accurate and not too computationally costly compared to some other things. And so that's kind of the game, and DFT is sort of trying to pick an appropriate functional for your problem that hopefully isn't too computationally expensive and hopefully gives results that are accurate enough for what you want. The computational cost of DFT on paper tends to be similar to Hartree-Fock theory. It depends a lot on what you use for the so-called exchange terms. If you use what's called exact exchange or Hartree-Fock exchange, then the cost will be quite similar to Hartree-Fock. If you don't, if you approximate the exchange term, then it might actually be more accurate than Hartree-Fock and less computationally expensive, which is really great. I think a lot of folks in the field are starting to think that mixing in some fraction of Hartree-Fock exchange is a good thing, even though it makes the calculation a little more expensive. And now let me briefly introduce these post-Hartree-Fock electron correlation methods. So the idea is that I'm going to write my wave function as a linear combination of all this stuff. What are these things? Well, C0 is going to be some coefficient, generally in the ballpark of 0.9 something, times a reference determinant, or the Hartree-Fock determinant that we've been talking about all along. So the wave function is going to be a large fraction, but not 100%, of this Hartree-Fock determinant, and then I'm going to mix in some small fractions of a bunch of so-called excited determinants or substituted determinants. And this notation means I start from my Hartree-Fock determinant, but I rip out an electron that was in spin orbital I, and now I pop it into a spin orbital that was formerly unoccupied and therefore unused in the original Hartree-Fock determinant. So I move electron out of spin orbital I and into spin orbital A, and because I've moved one electron or changed one spin orbital in my determinant, that's called a singly excited or singly substituted determinant. And that determinant gets a coefficient in front of it that has the same labels. I am not required to stop at only moving one electron. I could move two electrons if I wanted. That's the doubles. So you take electrons out of spin orbitals I and J and put them in spin orbitals A and B, and that determinant gets a coefficient in front of it. And I go on to triples, quadruples, etc., etc. Normally, I don't keep going out because there are more and more and more of these as you keep substituting more electrons, more spin orbitals. So frequently we'll stop at the reference plus singles plus doubles. Maybe we'll partially account for triples, and that's normally all that anybody can afford computationally because there are a large number of these substituted determinants. Okay, so I think I just said that bullet, and that bullet, and that bullet. Okay, so I've made these points. And just to illustrate these, in case this makes it a little clearer, here's an example of a singly substituted determinant. I took an electron, in this case an alpha electron, it could have been beta, out of this orbital, and I popped it up here, And so these orbitals used to be unoccupied, also sometimes called virtual orbitals in the Hartree-Fock determinant, but now one of them is occupied because I put an electron there. But you call these the occupied orbitals, the ones that are occupied in the Hartree-Fock determinant, and you call these the virtual orbitals or the unoccupied orbitals. So there I swapped one, here I moved 2 electrons. I don't have to pick 2 that are paired up. I could move one from one spatial orbital, one from a different spatial orbital. That would be fine too. But that's an example of a double. This would be an example of a triple. That would be an example of a quadruple. So I think you see how that works. Now, if I'm going to do this expansion, obviously I have to get these coefficients from somewhere. Somebody has to tell me what all these coefficients are. How do I get them? Well, you might have a guess about one possible way to do it. You could use the variational method because, again, we know that the wave function gives me an energy that's always higher than the true energy. So I could keep tweaking or varying these coefficients until I get a minimum energy and pick those as the coefficients. And that's exactly what some people do. If you do that, that's called configuration interaction, CI. These are called the configurations, if you like. And configuration interaction with singles and doubles means the wave function is this reference plus the singles plus the doubles, and then I chop it off and I don't go beyond that. And that's an approach that you can do. An alternative approach, which is generally more popular than the CI, is called many-body perturbation theory, and in this context also called Moeller-Plesset perturbation theory. And that's an approach where I use perturbation theory from quantum mechanics to get these same coefficients. And frequently I'll stop again at the reference plus singles plus doubles and chop it off there. And if I do that, then that can give me what's called MP2, Moeller-Plesset perturbation theory at second order. And in fact, normally in MP2, if I'm using normal Hartree-Fock orbitals, the singles wind up kind of dropping out and not contributing, which is a nice little simplification. Or I can go a step further and use what's called coupled cluster theory. This was developed first for nuclear physics and then borrowed for electronic structure theory. What you do there is similar in spirit. I again have a linear combination of determinants, but there I approximate some of the higher order terms like triples and quadruples with products of the lower order coefficients. Another way of thinking about this is saying that I take some of what I would get with perturbation theory and some of the terms through infinite order in perturbation theory. If I look at only single and double substitutions in terms of my amplitudes, at least, coefficients, then that gives me coupled cluster singles and doubles. And that will tack on sort of for free, if you like, or for minimal extra expense, some approximate accounting of the triple and quadruple substitutions. If I work a little harder and try to get a better description of the triples by including some explicit triples terms, then that gives me CCSD parenthesis T, meaning I have triples in there, but I haven't quite done them fully using the coupled cluster approach. So the parenthesis means I've kind of gone halfway there to get the triples. Basically, you apply perturbation theory to the triples here, but the full coupled cluster approach to the singles and doubles. This approach, hopefully you've heard of it because it's very, very good. Some people call it the gold standard of quantum chemistry because it tends to give very accurate results as long as you're not delving into certain problem areas like literally breaking single bonds and diradicals and some other things where then the accuracy can start to suffer. So let me see if I can kind of summarize all of this and mention one or two other things. Here's the computational cost versus the size of system you can go up to. And you need to take these sizes with a large grain of salt because there are a lot of other approximations out there that I haven't really discussed, particularly what are called local correlation methods, where you try to weed out some of those doubles and triples and look at ones where the electrons that are interacting are restricted to be close to each other in space. Because in principle, two electrons that are 100 angstroms apart really aren't influencing each other very much, and I can throw those out. So that can allow us to go to way bigger systems, but I'm kind of glossing over that for now. Let's say Hartree-Fock will call it a medium accuracy. You can do maybe 500 atoms with kind of normal Hartree-Fock without doing a lot of tricks. Semi-empirical, because you approximate some things, you can go to much bigger systems. I'm not sure exactly how big. Let's just call it on the ballpark of 4,000 atoms without going really serious about some extra approximations. Run-of-the-mill DFT with kind of based on a Hartree-Fock code. They share a lot of the same steps. We'll call again sort of 500 atoms unless you do some special tricks. MP2, maybe 100 atoms, although certainly with local correlation and other things you could go way bigger than that, but let's call it around that. CISD, that one, unless you're doing local correlation or something, you're down to about 30 atoms. I'll call it high accuracy, similar to MP2. CISD has a deficiency where its accuracy actually degrades as you go to bigger and bigger systems. So for really big systems, you'd prefer to do MP2 over CISD. A couple cluster methods I'll call very high accuracy, more like the ballpark of 30 atoms without local approximations. And there is something called multi-reference CI and multi-reference perturbation theory and multi-reference couple cluster. I'll call this sort of ultra-high accuracy. This is what you would use if you were breaking chemical bonds. But unless you've got some special tricks up your sleeve, it's hard to do more than about a dozen atoms of this, or else you're waiting a really long time for the calculations. So hopefully that gives you kind of a bird's eye view of how these methods compare to each other. Okay, so that's my brief tour of some of the methods of quantum chemistry. Hopefully that's been helpful in introducing a few new concepts, and I'll do some additional videos that go into some of those topics in more detail.